Standard 9 is very much related to what we were just working on um, in Standard 8, in that we're looking at transformations of functions. We're just going to look at it differently this time. So before, what we were doing was I was giving you an equation, and then you were graphing that equation based on the transformations you saw to a toolkit function. Or we also, instead of giving you an equation, I also may have given you like a starting graph and then said transform it this way, and then you did it. So here I'm going to give you the graph, and then it's your job to tell me what the equation must have been. So just a different way of looking at the same type of problem. So when you're looking at one of these, first of all, you got to identify what is the toolkit function we're working with, right? So anytime we see the V kind of action here, we know we're working with the absolute value. And what I think is never a bad idea is to go ahead and sketch out what regular absolute value graph looks like. And we know that it's just, over 1, up 1, over 2, up 2, and so on. And then left 1, up 1, left 2, up 2, right? And so this just gives us a nice reference to look at as we're trying to figure out what's happening with this graph here. All right, so what might be kind of nice is kind of start off perhaps with, y equals, now give yourself some room here. So with the idea that you very well may be, needing to add things in here, but just start with y equals the absolute value of x, and then ask yourself the question of, okay, what's different about this one? So for one thing, right, this bottom of the V, which is at the point 0, 0, is not at 0, 0 anymore, right? It's moved up 3 and left 4, okay? So let's just go through both of those, right? It's gone up 3, left 4. So if we go up 3, that is going to be indicated by plus 3 outside of the function, right? Because we're talking about the y values. So outside of the function, we're going to add 3. And since we're going up, we're going to put a plus sign because we know that vertical shifts are always, exactly like we would expect. Plus means up, minus means down. Now, if I go left 4, remember that that would be a horizontal shift. And so a horizontal shift is always kind of the opposite as you might expect, right? So left 4 means plus 4. All right, so that takes care of the shifts, right? So that lands us up here. Okay, but if that's all I did, that would just, look like this, right? It would not be facing the same way as the other one. It would not. There'd be lots of differences there. So we're definitely not done. So let's look at what else is happening. Well, for one, this thing is flipped over, right? And it's flipped over vertically, right? All the y values flip. And so if it's a vertical flip, remember that means that the negative sign goes outside of the absolute value function. And then lastly, we know that normally if you go right 1, you go up 1. You go right 2, you go up 2. Is the same type of movement happening in this one? Well, no. If I go over 1, I'm changing my vertical direction not just by 1, but by 3. So over 1, vertical direction changes by 3. If I go over 2, vertical direction changes by 6. So it seems like what I'm doing here is not only am I taking the negative of each y value, but I'm also going 3 times as much in the y direction as I would have been. So that would be a vertical stretch. By 3. And just to label all of these, right, this negative, remember, was the vertical flip. Now, I really encourage you, there's nothing wrong with using technology as a check of your work here. So by all means, pick up your calculator, type this in, and make sure you get something that looks just like this. And to make it really look the same as this, right, pay attention to the scale here. So you go from -10 to 10 in the x, -6 to 6 in the y, right? So then it really should look pretty comparable on your calculator screen as it is here. All right, so I showed you how to do that one. Let's take a look at another one here together. And this would be a good one to pause and try yourself, I would say. All right, so if you've hopefully given this one a try. So we know, of course, that we're working with y equals x squared, right? Y equals x squared, and we're just going to give ourselves a lot of space here, okay? Now let's think about what's happened. We know that we have gone normally, right? Normally y equals x squared, and I can go ahead and graph it. Goes over 1, up 1, over 2, up 4, left 1, up 1, left 2, up 4. I think that's good enough. So there's our y equals x squared graph. All right, so what's happened to it? Well, this point that was at the origin has moved up 5, left 3. Okay, so kind of similar to our last one. Up 5 would be a shift up 5. And then if I want to go left 3, okay, I need to give myself a little bit more space here. Let me erase this square. Use parentheses, so left 3 means plus 3 inside the argument. All right. Now, much like that absolute value graph we just looked at, this thing has been flipped vertically, right? So it's going down instead of up. So we know there's got to be a negative out here, right? So there's our vertical flip. All right, has there been any sort of stretch or compression? All right, so here's where we want to look at what's happening if I go over 1. Well, in the normal graph, my y value changes by 1 also, right? So in this graph, if I go over 1, well, it kind of seems like my y value is changing by half, right? If I go over 1, changes by a half. Okay, but at the same time, I'm not really comfortable making a call like that on something that's kind of at no man's land. So let's try another one. Normally, if I go over 2, I go up 4. Here, if I go over 2, my y value changes by 2. So I'm starting to think here that what's really happening is that I'm ending up with a vertical shrink, right? So I go over 2, up only 2 when or sorry, not up, but my vertical changes by 2 when I know it's supposed to be changing by 4. So I'm thinking 1/2 is what I want to put out here, right? For a vertical shrink or compression, however you want to say it. All right, so let's just confirm that, okay? So normally, in a graph of y equals x squared, if I go over 3, I would go up 9. You can't see it here, but we know 3 squared is 9, right? So let's see what happens. Over 3, my y value changes by 1, 2, 3, 4. Certainly looks like 4.5, right? Which would be half of 9. So I'm feeling pretty good about this 1/2 that I put in there. All right, so now let's move down to this next one. And again, I'd like you to try this before you check out my solution. All right, but I know that I'm working off of the square root. Here's my main points for the square root. All right, 0, 0, 1, 1, 4, 2, and 9, 3. All right, so what's happened to this thing? Y equals the square root. Well, I know that this starting point has moved to the right 3 and down 4. Okay, so right 3 means I'm taking minus 3 in the argument here. Right 3. And then down 4 means outside the argument, I put minus 4. Okay. Now some other things are going on here. Normally, square root takes off this way. Okay, but I see it's taking off the opposite way in terms of x values. So this one is a horizontal flip. So remember, if it's a horizontal flip, you put the negative inside the argument of your function. And the other, here's the really tricky thing about this. Remember that in order to see the true shift, you're supposed to have the argument in factored form. So I'm not just going to throw this negative sign in here. I'm going to throw it in there with parentheses around the x minus 3, right? So our rule is to see the true shift, the inside better be factored, meaning there better be parentheses in any common factor pulled out of there. All right, so we have that. Now let's see. When I go over 1, I'm going to usually go up 1. Right now, if I go over 1, I've gone up 2. Okay, so maybe that means I should put a 2 out here for a vertical stretch. But let's check more than just that. Normally, if I go over 4, I go up 2. So now if I go over 1, 2, 3, 4, I go up 1, 2, 3, 4, twice as much as 2. Okay, normally if I go over 9, I go up 3. So if I go over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. How much do I go up? 1, 2, 3, 4, 5, 6 exactly. So now I'm pretty confident that I should have a 2 right there, okay, for my vertical stretch. Right, and I forgot to label this, but this is my horizontal flip. All right, this last one's a little tough, and so I'll just warn you about that. So I'd encourage you to give this one a try, and might have to think about this one outside the box just a little bit. All right, so of course what we're looking at here is y equals x cubed, right? That's kind of y equals, and I'll leave lots of space here, right, x cubed. Okay, and then we're going to have to figure out what transformations go with this. All right, so let's go ahead and draw y equals x cubed. So when x equals 0, y is 0. When x is 1, y is 1. When x is 2, y is 8, right? 2 cubed is 8. X is negative 1, where y is negative 1. Negative 2 means negative 8. All right, so there's our y equals x cubed. All right. All right. So there we have it. Now, what's happened here? Well, it looks like this point hasn't moved at all in the left-right direction. So that means I don't have to add or subtract anything with the x, right? There's no horizontal shift. There is a vertical shift, right? It looks like it went up 1. So I think we definitely need to put a +1 over here. So vertical shift up 1. Okay. Now also, normally from this point you are going up on the right and down on the left, right? But we're going up on the left and down on the right. So that indicates to me a flip. Now it actually turns out with y equals x cubed, that could either be a horizontal flip or a vertical flip, and you would get the same result. But vertical always seems to be easier to me, so I'm going to go ahead and stick a negative out there. All right, so we've taken care of the, oops, we can't see that, can we? Taking care of the vertical flip. All right. All right, so lastly here then, definitely the shapes look different, right? This one seems wider or maybe more vertically compressed than this one. Okay, so let's try to see if we can make some sense of this. Because vertical just tends to be easier, let's see if we can work with that first. So normally when I go over 1, my y value changes by 1. So if I try that same idea here, if I go over 1, I can't even barely see what's happening with the black graph, right? And even if I go over here where there's nothing in the way, if I go over 1, I can barely see what's occurring here. Okay, so that's not very helpful. So normally if I go over 2, I go up 8. Well, if I go over 2, I go up some amount, but I can't really see what that is. Over 2, I can't really see how much that is exactly. So what's happening here is that we are trying to understand this from a vertical stretch or shrink perspective, and there aren't any clear points for me to really grab onto at this moment. So one thing we can do is look at it the opposite way. Instead of saying on the y equals x cubed graph what happens, well, normally I go right 1 and then change in y by 1. How about you start with the change in y? Okay, so if we start with the change in y, so when I go up 1 in the y, right, or I change my y by 1, how much do I change my x by? By 1, right? All right, so now let's try that here. If I change my y value by 1, how much have I moved my x by? Well, it would be by 1, 2, 3, right? So what that indicates to me is that I have a horizontal stretch by a factor of 3. Because instead of going up 1 over 1, like the normal graph, I'm going up 1 over 3. So I'm going horizontally more than I would have been. All right, let's try the same thing with 8, okay? So if I go, normally if I go up 8, I'm going over 2, right? So let's try it. 1, 2, 3, 4, 5, 6, 7, 8. So if I go up 8, how much am I going over? 1, 2, 3, 4, 5, 6. Again, I'm going over 3 times as far. So what we get here is this is a horizontal stretch by a factor of 3. Now, what do we put in here? Remember, horizontal is kind of the opposite of what you'd expect. So instead of multiplying by 3, you multiply by 1 over 3, right? And remember, the reason that makes sense is what we're saying is it takes longer for things to happen, right? So x is kind of telling you when certain y values occur, and by multiplying it by a third means it's going to take even longer for the same y value to occur in this transformed function. All right, so to kind of clean up my mess here, let's get rid of this thing. All right, so it's the, well, let's put that negative closer. So negative the quantity 1/3 x cubed plus 1. And again, put that in your calculator, make sure that it works. There's nothing wrong with that at all. But this one here, if that made sense to you, this would be kind of the challenging one to look at here, because of the fact that those horizontal stretches and shrinks can be